Okay, so here's our notes. You should definitely, I don't have it in front of me, but go back and look at the calendar. And I would, again, just as my suggestion, go ahead and write our quiz and your day of the test that you're going to take it, right? The quiz is going to be online on Blackboard. The test will be in person. Okay. The notes here are due when we take the test. So Unit 6 notes are due the day of Unit 6 test. All right, please make sure that you have your name on it. Okay. They are very long, lengthy, right? But I know I've said it multiple times. I'm going to say it again. This is 2 units combined into 1. That's the reason why. Now let's go ahead and start off with this. Actual notes are broken into 2 units. It's momentum and impulse. And then the second set of notes is going to be work, power, and energy. Okay. So let's start off with momentum and talk about that. It says here that what is momentum? Because I'm sure you probably heard that word, used it before, but were you using it correctly? Or when you heard that word, was it used correctly? Momentum is the measure of how difficult it is to stop an object. Okay? How difficult it is to stop the object. Momentum is closely related to inertia. It is the product, so product means multiplication, of the object's mass and how fast it's moving. Momentum is commonly used in sports. When a sport announcer says that the team has a lot of momentum, they mean that the team is really, quote unquote, on the move. Right? They're winning. They're doing good. And is going to be, here's really what they should be meaning, hard to stop. Because that's the definition, is how hard it is or how difficult it is to stop an object. Any object with momentum is going to be hard to stop. Okay. Let's keep going. It says here, though, the bigger something is, the more momentum it's going to have. And the faster something is, the more momentum it's going to have. Okay? Let's go ahead and do our equation here. Momentum is lowercase p equals lowercase m times lowercase v. So lowercase p, not capital P, because capital P stands for something else. Lowercase p stands for momentum. The SI unit for momentum is kg dot m/s. You'll see it at times without the dot, because when 2 variables are right next to each other, what does it mean in math? It means multiplication. Okay, so kg m/s. V stands for velocity. And if I look at my SI units, ms is going to be my velocity, meters per second. So that means that it needs to be in meters and in seconds when you're doing the velocity. And mass, just like any other math equation in physics, if it has mass involved, it must be in kilograms. Okay, I'm going to go ahead and place this into the triangle because I love using that triangle just to help shortcut my algebra. Right? We all remember that this line means division and this line means multiplication. So if you come over here to our equation, cover up the equals part, mass and velocity are being multiplied, so they have to be at the bottom. What's left over? P. And so in this case, you can just cover it up. Velocity equals P over M. M equals P over V. P equals M times V. Okay? So again, hopefully that helps you out. Let's look at some of the practice problems. Okay? It says here, which bike rider has the greatest momentum? Don't forget, to have more momentum, you have to have more speed or more mass. We've got a 40 kilogram person riding 45 miles per hour or a 50 kilogram person riding 45 miles per hour. Now they both have the same velocity, so that variable doesn't even count. The only variable that's important to us right now is going to be the mass. This one has more, so the 50 kilogram person is going to be the one who's going to have more momentum. Next one. A ball is moving with a velocity of 30 meters per second and a momentum of, lowercase p, 15. The mass of the ball is, question mark, M. So let's come to our triangle, cover up M. Let's write M equals P over V. P over V. So in this case, P is momentum of 15. V is 30. So 15 divided by 30, okay, equals 0.5 kilograms. And that's my answer. Not too bad, huh? This is a really easy equation. It says here that Grant is playing baseball and has a 5 kilogram ball. That's the mass of this baseball. He throws the ball with the velocity of 22 meters per second. What is the ball's momentum? Question mark, lowercase p. Well, in this case, if I'm looking for momentum, I'm going to use the equation as is, and I'm not going to have to rearrange it. So let me write that down. P equals M times V. Mass is 5 and does not have to be converted. Velocity is 22. So 5 times 22 comes out to blank. And what's my SI unit for momentum? Kilograms times meters per second. Okay. I know you can plug that in yourself. The next one says here that a boulder has a momentum of, so this is the boulder's momentum, lowercase p. And if it's moving at a velocity of 2 meters per second, what is the boulder's mass? Question mark M. Going back to my triangle, cover up M, and let's write down M equals P over V. P over V. Or 200 over 2 equals blank kilograms, because that's the correct SI unit. Okay? So here's some practice. Hopefully it helps you out. There's 2 more practice problems over here. You need to practice some on your own, but we can definitely go over them when we have in-person class. So I'm just going to put a little highlighted. Make sure you get those done. The next topic we're going to talk about is impulse. Okay? Now, I know you have heard that word before. You've used that word before, but were you using the word correctly? Okay? That's what our goal is. Our goal is to make sure that we actually not only, hear the word and we say the word, but we want to make sure that we use the word correctly. So when it comes to impulse, it says here that the definition for impulse is a change in momentum. That's what impulse is. Probably, you probably have heard it or used it as a term as, oh wow, they don't have any impulse, or look at their impulse. They're just going to quickly react. Okay, that's how the majority of people use it. But in physics, it's a change in momentum. Now it says here though, with inertia, you know that an object in motion will stay in motion. Which means that it has momentum because it's moving. and it will remain the same. It says here though, in order to change the momentum, or motion, you must apply a force. Hopefully we all agree to this. Right? We've talked about this, we've learned about this already. So if an object's in motion, it's going to stay in motion. Newton's first law tells me that. And so since it's moving, it's going to have momentum. And that momentum is going to stay the same as long as it's moving. Right? Because unless there's an outside force acting on it, it is going to move in a straight line at a same constant speed. So the momentum is going to stay the same. But if I want to change that momentum or change the motion of that object, then I need to apply a force to it. So hopefully we all agree to that. So impulse is the change in momentum or the force and the time it takes to apply that, to cause the change. Okay? So if I'm going to cause a change of momentum, then hopefully we all agree that you're obviously going to have to apply a force to that object, and you're going to have to do it for a certain amount of time. Okay? So that way you can cause the motion to change. It says here though, to stop an object that has momentum, it's necessary to apply a force against the motion for a given period of time. The more momentum that an object has, the harder that it is to stop. Thus, it would require a greater amount of force or larger amount of time, or both, to cause that object to come to a stop. We're back to equations again. So let's go ahead and let's look at the equations that we've got. Impulse is capital J equals capital F times T. Impulse is capital J equals F times T. That's our equation. Again, it's a 3-variable equation, pretty simple. Capital F stands for force, and we know that, which is in newtons, right? The next one is T, which is lowercase t, which stands for time, because a capital T stands for period. And the SI unit is in seconds. And then the J is impulse, right? I don't know why they're not using, and I don't know why I put an I there. I do not know why they are using J instead of the letter I. Who knows? I do not know what the madness is behind that. Okay? And the SI unit for impulse is kilograms times meters per second. Whoa. Does that look familiar? That's the same SI unit as momentum. Okay? That, one more time, is the same SI unit as momentum. Now, this can be put into the triangle, and I love the triangle, so let's go ahead and do that. Cover up the equal part. Force and time are being multiplied, so F and T. And then let's write in what's left over. And now we can rearrange it algebraically a little faster. It says here, though, how does the impulse relate to momentum? Obviously, there must be some relationship, because if there wasn't, then why do they have the same SI units? So there's some type of correlation there, and we're going to start talking about that. It says here that a force acting for a given amount of time, which will change an object's momentum. Okay? And believe me, we're going to get into this a lot more because that's a whole nother equation. It says, though, here, though, it says, in football, the defensive player applies a force for a given amount of time to try to stop the offensive player. So they're getting into a few examples. It says here, though, you have also experienced the magnitude of times while driving. So you experience impulse and momentum while driving. As you bring your car to a halt when approaching a stop sign or a stoplight, the brakes serve to apply a force to the car for a given amount of time to change the car's momentum. So the brakes are doing the job. You have to apply the brakes for a certain amount of time, and then eventually that force, for however much time that you are applying the brakes to the car, is going to cause the change in the car's momentum. Hopefully we all agree with that. Now, an object with momentum can be stopped if a force is applied against for a given amount of time that is equal. Okay? So what they're trying to say here, especially for the car one, and we need to understand this one here, is that some of you may be driving already, but for those of you especially who are driving, even if you're not driving yet, you've been in the car and then all of a sudden something, or you didn't pay attention, or somebody or a car or a cat or dog got in front of you, and immediately you have to apply the brakes. How do you apply the brakes? You apply them very quickly, right? So when you do it very quickly, there's a little amount of time that you applied the force to cause the momentum to change so it can come to a stop. How did it feel? Right? Some of you, right, you call it brake check. How does it feel to brake check somebody if you're going quite fast and then all of a sudden you instantly hit the brakes and then quickly you come to a stop? Compared to you're driving whatever speed, but you slowly apply the brakes to the car and the car comes to a slow, easy stop. Now, don't get me wrong, though. It takes more time to come to that slow stop. But it's going to feel differently compared to the short amount of time when you slammed on the brakes. Okay? So keep that in mind because we're going to talk about that part as well. Now, it says, let's have a couple of practice problems. Not a problem. A car is moving at a constant speed when the driver hits the brakes. The brakes exert a force of 20 newtons for 5 seconds. What is the impulse? So this is pretty easy. Plain Jane, we're looking for the impulse, so we're not going to rearrange the equation. J equals F times T. We have the F. If we didn't, we would have to solve for it. We have the T. Yes, we do. So 20 times 5 equals blank. What's my SI unit? The same SI unit as momentum. Kilograms times meters per second. Okay? Let's keep going. It says over here that a cyclist is traveling at a constant speed, then applies the brakes for 3 seconds. That's T. If her brakes exert a force of 17 newtons to the tires, what is her impulse? Well, impulse equals F times T. So in this case, F is 17, T is 3. All of the numbers were given to me, which is nice. I don't have to change anything. But my SI unit, don't forget, is the same as momentum because they're related to each other. And that relationship between the two actually causes another equation that's going to come up. Okay? So let's look at the other equation that's here. So let's go through this one more time. Momentum is how hard it is to stop an object. Okay? If it's moving, right, and it has mass, then it has momentum. What about wind? When wind is blowing, does it have momentum? Yeah, because the molecules, the air molecules, have a mass. It may not be a lot, but it does have a mass. And when it's moving at a certain velocity, it's moving. What about when tornadoes come around? That's pretty rough. That's a lot of momentum from the wind. Okay? Now, impulse is another word, and impulse means the change in momentum. So, how do I change momentum? I have to apply some kind of force, friction, applied force, you hit the brakes, I don't care, but some kind of force to cause that object to come to a stop. Not only that, but you apply that force for a certain amount of time period, which then is going to cause it to stop. But how is it going to stop? Is it going to stop really fast, or is it going to stop very slowly? And due to the amount of time that it takes for it to come to a stop is going to determine how that stop is going to feel. Is it going to be a rough one, or is it going to be an easy stop? Okay, so keep that in mind. Let's go ahead and go to the next equation. Knowing that those two words are related to each other, in physics, this is awesome. I love this equation. Because both of them are related to each other, we can set them up equal to each other. So we can say that J equals P. Okay? But we can we can change it if we need to. We can say, how about over here? Ft equals mv. We changed the J to an Ft, and we changed the P to an mv. But wait, I love this part. They all mean the same thing. What if we change it again? What if we say Ft, which is the same thing as J, equals P? Whoa. I love this. Let's do it again. What if we say J equals mv? J equals P is changed to an mv. This is so amazing. And because they are completely related to each other, if I know one, I can solve for something else. And I can set them up equal to each other. This is the equation that students get confused, because this equation, if I recall correctly, and let me go ahead and pull up the formula chart. Oh, no. I'm glad I looked it up before I said anything. This equation is on the formula chart. It is one that's a little tricky for students. Force times the time equals mass times velocity. Okay? So here's the momentum equation. Here's my impulse, which is J equals P. That's the combination. And you need to know in your head that J equals F times T just by itself. Okay? So 1, 2, 3 equations. Alrighty? They're here on the formula chart for you. Alright, so let's keep going. V stands for velocity, which is in meters per second. M stands for mass, which has to be in kilograms. F stands for force, which is in newtons. T stands for time, which is in seconds. Okay, those are all of our variables. Could I put this into the triangle? I absolutely cannot. Okay, I can't put that into the triangle. I'm sorry. I apologize. But let's practice. Okay? Because this equation is going to need some practice. It says here, though, that Jennifer, who has the mass of 50 kilograms, that's kilograms, not pounds, so that's a good number, is riding in her red sports car that's traveling at a velocity of 35 meters per second. Right? She must suddenly slam on her brakes to avoid hitting a deer crossing the road. She strikes the airbag, which brings her body to a stop, and it took this much time to come to a stop. What is the average force, force, does the seatbelt, I should say airbag, applies to her? Okay? So They gave you the equation over here and told you this is the equation you're going to use. All right, but I'm just going to go ahead and write it out just as a generic J equals P. Alrighty. Now, do I have all four variables so that way I can plug it into here? I have 1, 2, 3, and one that I'm looking for. So I actually do. So in this case, I can use this full-on equation, which is Ft equals mv. And it doesn't matter how you write it, right? You can flip them, all right? They're equal to each other. So let's go ahead and let's plug it in. F is my unknown variable. T is 0.5. M is 50. V is 35. Okay. Now I know y'all have got algebra skills because y'all wouldn't be here if y'all didn't have it. So let's use our algebra. If we divide by 0.5, this cancels out. Divide by 0.5. So F equals blank newtons. Plug this into your calculator. Okay. Let's keep going. It says here though, imagine that a 100-kilogram car is moving 20 meters per second and comes to a stop. Whoa. This is my initial velocity, and it comes to a stop is my final velocity. We're going to go back to those variables, but I'm going to go ahead and I know that this equals 0 because it came to a stop. The momentum goes from 2,000 to 0. So this is my PI and this is my PF. Okay? I just want to go ahead and just lay out and label all my variables that they gave me. So the impulse or change in momentum is 2,000, right? Because it's from 2,000 to 0, which is my P. So if the impulse or change in momentum is 2,000, let's assume that it took 5 seconds for the car to come to a stop. T equals 5. What is the force on the car? Question mark F. Okay. They gave me a lot of variables. And when you get a lot of variables, sometimes that's a clue that, you know what, you're probably going to go ahead and use this extended equation, this equals to. But for some of us, let me go ahead and label or write out all of our variables. I've got mass that they gave me of 100. I'm looking for force. T is 5. Velocity is 20. And they even told me that P is 2,000. Okay. So that's all the variables that I have, and I'm looking for force. Which side is force on? Force is over here on the J or impulse side. Okay. So because it's on this side, I'm going to have to write out my equation. Instead of using J equals P, okay, I'm going to have to change it up, especially this side, the impulse side, because I'm solving for F. I'm going to say F times T equals, do I have to write out the M and the P? I'm sorry, the M and the V? I have those variables, but I actually don't have to write them out because I know what the P is. So I can just say equals to P because I know that P. Let's plug it in. F times 5 equals 2,000. We're going to use our algebra. Divide by 5, cancel, divide by 5. F equals blank newtons. And we're done. Hopefully that wasn't too bad. Okay. I do believe that we have to practice though. All right. Now I'm going to stop there because I definitely want to talk about those equations in class together. I'm telling you that you should go ahead and try this on your own first. See how you do. But this needs to be in class kind of thing to talk about and go over it. Let's go over a little bit more notes, and then I'm going to pause this lecture here, and then I will go back and video some more in a little bit. But the next part here, when it comes to impulse and momentum, is what we call the crumple zone. Okay? So the crumple zone says here that you can see that if you increase the stopping distance or how long it takes to stop, then it's going to cause a decrease in the force on an object. This is why modern cars have what we call a crumple zone. Okay? Now, mathematically, when we come to class, I'm going to show you mathematically, but this is already kind of common sense to you. You know that if somebody's going to brake check you and you're in the passenger seat and you are not ready, they immediately hit the brakes and they stop very fast with a little bit amount of time. How does it feel on your body? Very rough. It's like you're going to break your neck, right? So the force is very high, okay, with a little bit amount of time. But if you, before you get to the stop sign or red light, start coming to a stop by slowly hitting your brakes, increase the amount of time it takes to come to a stop, you're going to decrease the amount of force because, like, you don't even feel that force onto your body. It's really easy. So crumple zones are the area of the car that's actually designed to crumple on impact. In order to increase the amount of time it takes for that object or the car to come to a stop, okay? Rather than brake checking and breaking your neck over there, all right, we're trying to help you out by building and creating what we call these crumple zone areas, okay? It says here, though, airbags use the same concept as that crumple zone. I mean, they didn't have airbags a long time ago. And they actually increase the amount of time that it takes for your body to, for the impact to decrease the amount of force from the car onto your body. Okay? So a long time ago, they didn't have any kind of airbags or any kind of seat belts. Finally, due to Newton's first law of motion, and I'm sure that's not what they said when they came up with seat belts, but seat belts were there to help increase the amount of stop time that it took for your car to come to a stop, so that way you can decrease the force on your body. But mainly, seat belts are there due to Newton's first law of motion, that an object in motion is going to stay in motion. If you didn't have that seat belt and you got into a wreck, you're going to continue to fly forward out the windshield, all right, and not survive it. Then after seat belts, okay, they started figuring out that, you know what, even though people are in car wrecks, they're really still getting hurt. They're breaking arms, bones, legs. Some of them are not surviving. Like, literally, they can't survive it, right? So then they started coming out with airbags. And so